fine Wednesday. Hopefully well. Um, all right, so what I wanted to do today was basically just Q&A. So I've got, you guys of course have a big pile of exercises to work on through Edfinity. And so I wanted to make sure that we had some time for questions. And since we're basically done with material, so let me have it. What do you guys what questions do you guys have? So either hop in the Discord channel so I can hear you, or just type in the stream chat. Like a particular problem that you number that you want to look at, and I've got Edfinity loaded, and I can switch the screen over to it as needed. So yeah, we're almost to the bitter end, guys. This whole stupid online teaching thing is almost over. I'm definitely ready for it to be over. I'd much rather be in the classroom with you guys. All right, number 9, homework 5.3. Yes, okay, so let me first off open it so I know what it is. I don't remember all of these. Um, okay, so I'm going to switch over to the computer just so that we can all see the problem. Um, all right, so problem number 9 is this one from 5.3. So it's we're going to work with the integral of -1 to 1 of 5x squared dx. Um, and we want to do this with the Riemann sum sort of method. And we want to find the above integral using n subintervals and the right-hand rule. So we'll enter a formula involving n. And then once we've got that, the next three boxes are just plug in n equals 10, 100, 1,000. And then the idea there is then we can kind of see what the limit ought to be, and then we'll of course look at what the limit really is. You guys might have different numbers for like where the 5 is or the -1 to 1 part. Um, so some of this may be slightly varied. All right, so I'll go back to the iPad so that we can work this out. Um, all right, so oops, yeah, there we go. Okay, so we were dealing with the integral. It was integral from -1 to 1 of 5x squared dx using n right-hand rectangles. Okay, so if we just kind of sketch out the picture, we've got a parabola. Say here's -1 and 1, and um, we don't really need to sketch the picture other than it helps maybe coming up with the formula a little easier. So if I divide this into, I'll just for the sake of the picture divide it into three pieces. Then for the right-hand rule, well, first off, our delta x is going to be b minus a over n, which is 2 over n because the width of the interval from -1 of 1 is 2. Um, and then for the right-hand rule, basically we leave off the first point and we only do all the subsequent ones. So the area is going to be the sum from k equals 1 to n of uh, the width times the height. Okay. All right, so let's make sure that we're clear on the three parts that we've written so far. The 2 over n times f of something is going to be the area of an individual rectangle. Okay, the f of something will tell us the height of it. We'll figure out exactly what that term looks like in a moment. The width we already said was 2 over n. And then the sum goes from 1 to n here because we're doing the right-handed stuff, not the left-handed stuff. Um, the left-handed version would go from 0 to n minus 1, right? So it's just which point are you leaving off, the first one or the last one? Okay. All right, so we clear with that part, and then we'll fill in what the f of whatever needs to be. That's the next thing. Um, okay, so the f of whatever is going to be -1 because that's our a. Okay, so that's the left-hand end of things, and then plus uh, k times our width, which was 2 over n. Okay, so the way that we should think about this is that when k is 1, we start one width unit away from -1, which would be here. Okay, and that is the first right-hand side of the rectangle that goes with it. Okay, and why -1 here? It's because we're starting from the left and moving to the right, um, because our sum starts at 1 and ends at n. Okay, so are we Gucci with that setup? Obviously, we've got more to do. Um, yeah, Nate, did you have that set up? Okay, Willie, you're good. Nate, hopefully you're good. Well, good. I got most of you guys here this morning. All right. So, in our case, the function was 5x squared, so we can replace um, we've got 5 and then the stuff that, okay? Um, and so now what we've got to do is we basically have to just FOIL all this crap out and get this in terms of a function of n only. Um, because I'm lazy, I'm going to have Mathematica FOIL all the stuff out for me, just so I don't botch it. So hang on one second. And I'm going to have it expand that. Okay, so I just did the foiling part with Mathematica, um, and what we end up getting is 40k squared over n cubed minus 40k over n squared plus 10 over n. Okay, so do you guys buy at least that part? Right. I mean, I'm being lazy here just for the sake of time. Um, okay, so now what we have to do is simplify each of those three expressions using summation rules to basically get rid of the sigma. Okay, so actually, I'll let me rewrite this one more time, and I'm going to rewrite it like this. So the first term uh, was 40k squared over n cubed. Um, I can pull out anything that doesn't involve k. So I can simplify that one. And then the second term, I'm going to pull out anything that doesn't involve k. And then the third term, nothing involves k. So that just leaves um, this. Okay, so are we cool with me splitting it up that way. Is that Gucci? Because at this point now we can throw our summation rules at it. So let me just kind of over here on the side remind us that if we have a constant added up, then this is just a fancy way of saying multiplication. And then um, this one was the form. Oops, sorry, not k. It should be n. Okay, so that was the clever trick that we discovered when we were adding up, say, the numbers from 1 to 100, right? We pair them off sort of from the outside in. So it's, 1 plus 100, in, uh, and that's 101. 2 plus 99 is 101. 3 plus 98 is 101, etc. And then there were 50 pairs. So it's the amount that each pair adds up to times the number of pairs over 2 because we did it in pairs. Um, okay, so right, so we had that formula, and then the k squared one turned out to be n times, oops, n plus 1 times 2n plus 1 all over 6. That one's a little harder to prove. Um, why it's that, but so you guys can just take my word for it um, for the sake of this. It is interesting, actually, that Archimedes proves that result, although um, uh, it sorry, lost my train of thought. Um, Archimedes actually proves that result, although it looks rather different in the way he proves it. Um, um, yeah. So anyway, just FYI, that's kind of an ancient result. All right, so once we have those three things, now we're pretty much ready to go because we can just replace each term with with its corresponding answer. Okay, and in this case, since I pulled out the 10 over n, then this here is just the n. This here was that term, and this here was that term there. Okay, so we good with that? Any question, preguntas, fragen? Hopefully. Okay, so that thing is our formula for n. Okay, and we could probably simplify a little bit. If we like, we can maybe cancel some stuff so it looks like we got some n's that cancel in each term, and yeah, so we could simplify this expression a little bit. Let's just go ahead and take care of the low-hanging fruit, namely the n's. So we'd have 40 over 6 n squared. Well, that fraction looks terrible. Let's try this again, shall we? 40 n plus 1, 2n plus 1 over 6n squared. And then the next term would be, well, we'll have 20 n plus 1 over n, and then just plus 10 at the end. Okay, so we could simplify that a little. Oops, sorry. Let me scroll up a little. We could probably simplify that a little bit more, but I mean that is a formula involving n only, so there you go. Um, okay, so then the Uh, next three parts, which were basically just plug in this for various values of n, that should be easy, right? You're just you've got the formula and you're just substituting n equals 10, 100, or 1,000, and just computing what you get. So that I think you guys can handle. What I would do there, because I'm lazy, is I was just define this thing as a function in Mathematica and then tell it to evaluate it at 10, 100, and 1,000 and be done with it. And then have it do it as a, express it as a decimal, just for rounding purposes. Okay, but then the real question is what's the limit, right? So that's where the fun part is. And so um, let me call this, actually, let's call it, let's call this answer that we got r sub n for right-handed rectangles with n of them. And so then the true area, or the true value of the integral rather, um, is the limit as n goes to infinity of r sub n. And then I'll just copy this thing here. Okay. Isn't modern technology wonderful? And so we just need to take the limit of that thing. Now, the far right-hand term is easy because the limit of a constant is itself. Then the other two terms are going to require a little bit more mental gymnastics. Um, so if you guys remember probably from high school or way back in the semester, I mean, this goodness would have been in February probably, when we were talking about limits initially. If you're taking a limit at infinity, then the trick basically is you just get to look at the leading coefficients if the powers are the same on top and bottom. So if we look at the first big fraction there, uh, if we were to FOIL all that out, the biggest power of n that we would get would be n squared. It would have a coefficient of 80, because we've got the 40 that's out front and then the 2 that's inside the second term. So we'd have on top basically 80 n squared plus stuff, and then on the bottom we have 6 n squared. So this term is going to go to um, 80 over 6, the ratio of the leading coefficients. Then the second term, we don't really have to FOIL anything out there. The biggest power of n on top and bottom is n to the first, and the coefficient on top is 20, and the coefficient on bottom is 1, the ratio of which is just that. And then we have, of course, the plus 10 at the end. And then, we can simplify that, but that is going to be the limit. Okay, so is that part good? And then just for the sake of um, that is equal to, if you simplify, this is equal to uh, 10 thirds, um, which of course is 3.3 repeating. Um, yeah. Um, okay, so I just did a quick calculator thing there. Now we can double check our answer to make sure that this is correct, because now we also have the fundamental theorem. So we could have, of course, done it that way. Uh, just as a check here, right? The point of this problem was to go through it the Riemann sum method, um, just to make sure that we understand the setup for the Riemann sums. But of course, since we know the fundamental theorem, it would be silly for us to not take advantage of that for the sake of double checking that we are getting the correct answer. All right, Nate, does that clear that up, hopefully? Uh, and the answers for when you plug in n equals 10, 100, 1,000 are going to be close to this 3.3 repeating. They won't exactly equal it, obviously, but they'll be sort of getting closer to it. That's the whole point of a limit. So, um, right. Okay, excellent. Yeah, that was a fun one. These Riemann sum questions do take a little bit of time, um, and number 10 on this assignment is going to work pretty much exactly the same. However, there is, I think, one thing that I need to give you guys for number 10 that I forgot about. So it's a good thing that we brought this up. Let me go over to another page. So basically, here on the right, we have those three summation formula. Um, that gets us basically uh, constants k and k squared. But if you look at the problem in number 10, it has a k cubed, or sorry, an x cubed in it, which means that when you go through this Riemann sum process, you're going to end up with a k cubed. And I haven't given you the formula for the k cubed term. Um, you can't just look it up. It actually is kind of cool what it turns out to be. Um, so it turns out, okay, so this is for 5.3, number 10. Use that the sum of k cubed from 1 to n, it turns out to be that. N times n plus 1 over 2, whole thing squared. Um, and I am most certainly not going to try and prove that to you guys, so just take my word for it. But you will need that summation formula in order to do number 10. But otherwise, number 10 will go pretty much exactly the same way that we just did with number 9, because you're using right-handed rectangles again. It's just a different function this time, and the algebra will work out a little bit differently. But the idea is basically the same. And then for part C, obviously, whatever the integral is by means of the fundamental theorem ought to be what you get for your value of the limit when you set it all up. So, okay, so good question. What's next? Oh, and this k cubed summation formula, I'm sure it's in the book. I probably just forgot to mention it. Um, and you can always look these things up. Um, I happen to have a bunch of them memorized, but only because I teach this stuff all the time. Um, all right, good question, Nate. And so, what other questions do you guys have? I feel like I need to set up a thing where I can hit a button and it'll start playing Jeopardy music for the stream. Could probably do that. Be sure to like and subscribe so I can make affiliate and start getting, lots of sweet ad revenue. Seriously, no other questions? It's going to make me a sad panda. It looks like we got most of you guys here. Even it looks like Dr. Gates has joined us this morning, so shout out to Buck Nasty ZB. That's Dr. Gates. Um, we can all rate his channel later when he's teaching calculus. So, um, so maybe in addition to the Jeopardy music, I need to have like crickets chirping as a sound effect to the stream. Yeah, right, Mia. We need to have crickets chirping. So, my puppy is sitting here waiting for another question. Can you go over what we'll be doing for the quote final? Um, you won't. Your final, there is no final. Um, basically, the last problem set, um, so the substitution stuff, I made that do in place of the final. So yeah, basically all you guys have for the um, is the so let me go back to actually the iPad for a second. This will be helpful. Um, where did I put the magic switcheroo thing? Full screen. Here we go. Okay, so the basically I posted 5 assignments, right? So we had the Euler's method assignment, the definite integral assignment, and I realize my camera's getting in the way. The Riemann sum assignment, which we just talked about some, the fundamental theorem of calculus assignment, those all 4 are due Friday. So when I assigned these, what goodness, it was the beginning of last week or maybe the end of the week before. Um, Rather than staggering them out, one due one day, one due another, and so on. Just because I know it's a little crazy here at the end, I just made them all due Friday. Those 4, and then the 5th one, the substitution, U substitution assignment is due next week, basically when our final would have been. And that's it. Yeah. So I was hoping to do a project with you guys, but it just was going to be too much in too little time and so on. So, thanks coronavirus. I feel like that's going to be 2020 versions of thanks Obama. So anyway, all right. So the next question was number 12 on 5.4. So let's look at that. Yes. Okay. All right. So let me write these out. Um, So, uh, so number 12 is basically, I'm going to go back to the iPad, but let's just recall the integral from a to x of f of t dt. If I call this fatty f of, well, here, let me rewrite this. Um, if I define fatty f of x to be this, or that, sorry, I need coffee, is that, okay? And then also we had, if we defined f of x equals um, the integral from a to some function of x, then we have to obey the chain rule. Okay, so if we look at, we've got basically, I just noticed it has 2-part C's. That's kind of hilarious. Okay, Sorry, my microphone just decided to go nuts for a second. Um, all right, so we have the chain rule basically. All right, now if we look back at the problems in question here, the first one is going to be easy. So we've got um, f of x was given to be 5 to x. Sorry. The integral from 5 to x of 1 over t dt. Um, then fundamental theorem just says if it's from a number to x, you just plug in the x to the thing that was integrating, and that's literally it. Now, where this will get a little bit more fun is on the next part or the parts after that. Okay, so now in this particular case, um, that's the easy F2C way. We could have done this another way, which is to say um, that the antiderivative of 1 over t is natural log absolute value of t from 5 to x equals natural log of absolute value of x minus natural log of 5. And then if we take the derivative of that, we just get 1 over x, which is, of course, the same thing that the easy way gets us. Okay, so this would be to use the other version of the fundamental theorem. It is worth mentioning that the hard way um, of finding an antiderivative in some cases is not even possible. Okay, so in this particular case, the function 1 over t, we do know its antiderivative. It's just the logarithm. If we didn't know what the antiderivative was, then we would be SOL um, to try and do it the hard way. And the only thing we could do would be the easy way. Okay, so then to go on to part B, oops. There we have a slightly different version. Here, it's in the wrong order. Okay, the constant's on the top, and the x is on the bottom. Well, what would happen? So what needs to go in front if I switch the order? Okay, so I just switched the order of the integral from being x to 1 to now 1 to x. What does that change the answer by? Okay, so I've left space out front. I need to put something right there. What needs to go right there? Yeah, it changes it by a factor of a -1. Okay. Um, so, um, right. So then if our function is this thing, then the function's derivative would be negative the derivative of this guy. And um, that guy's derivative by the fundamental theorem is 1 over x. And then, of course, we've got the negative in front. Okay, so in this case, it's just off by negative. One of the things that I think confuses students on this particular thing is that, like, let's contrast this with, um, oh, sorry, this is actually a good point. Contrast this with part A. So I actually just realized I miscopied it, that the problem actually was the integral from 25 to x. Um, but if you notice, the constant actually doesn't matter. It sort of disappears from this whole thing. So in this current problem, right? We had the integral from x to 1. It could have been the integral from x to a billion, and it's still, or the derivative of it would still be this negative 1 over x. Okay, so the value of that constant actually doesn't matter because we're taking a derivative, basically. Okay, so then for the other two parts, or for part C, and I just noticed here there are actually two part C's, they're just mislabeled. Um, for the first part C, it'll work basically like in part B, except we have to deal with the chain rule. Um, so there we had 13 to x to the fifth of 1 over t dt. And of course, your constants here may be slightly different. But in this case, it's just going to be 1 over x to the fifth times the derivative of x to the fifth by the chain rule. And in this case, it would just be a bunch of stuff cancels, and so we just happen to get 5 over x here. Okay, so let's just be clear. This term needed to be there because the function of x was not just x; it was x to the fifth. Okay, so the chain rule still applies here, and so there we go. So that's why I multiplied by the 5x to the fourth from the chain rule. Okay, now part D is more fun. Um, oops. Because there we had the integral from 2 plus cos x to x squared plus 1. Okay, so the problem here is there is no constant. Okay, so what we need to do first is let's split the integral into um, two terms. So let's take it from 2 plus cos x up to some number a, and then go from a to x squared plus 1, like so. Um, and then each of these pieces we can deal with similar to the pieces before. So for the first one, the first thing I do is flip the order. And then for the second one, I don't have to flip the order. Okay, and now that we've got it in that form, we can just do the fundamental theorem to each of the two parts. Um, again, remembering that we'll have to use the chain rule for both of them because the thing at the top of the integral, 2 plus cos x or x squared plus 1, both of those are not just x, they're functions of x. Okay, so does that make sense, Mr. Young? Hopefully. Um, that splitting it in the middle kind of thing with that constant a. Um, and I really could have put any number in place of a. I could have just written 0. But since the constant itself doesn't actually matter, um, then I can just put something as sort of a placeholder, and that's sort of the end of it. Okay, good. So what else? What other question, preguntas, or fragens have you guys? Um, just by the way, while somebody's typing or whatever, this is exactly what I want to do on Friday. I suspect that you guys are going to have problems with the U substitution. Um, oh, you know what? I seem to remember there was something that I asked you guys to do for today. Um, that I said we would talk about first thing. Um, what was it? Oh, that's right. Here. It was the integral of cotangent and the integral of cosecant squared. Um, sorry, I completely forgot about that. Um, so, do you guys have any other questions for now, or we can do those two problems that I gave you last time? Completely forgot about them. So I'll take, if you've got another question, I'm happy to do that first. But um, if not, we can do these two integrals that I asked you guys to look at. No? No other questions? All right, well, let's take a look at these two integrals, which will actually be good because they both involve u substitutions. So let's start with the integral of cotangent. Um, first step, oh, sorry, 5 on 5.3. All right, let me go back. Ah, okay. So we'll come back to this. All right, so 5.3 was um, we'll come back to it, Willie. Don't worry. 5.3 number 5 was basically we had 1 minus e plus e squared minus e cubed plus dot 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 all the way up to e to the 12th. And we were supposed to write that in the form I equals 0 to b of a sub I. Okay, so basically we just have to figure out the pattern here. Well, first off, how many terms are there? There are 13 terms, and so b should equal 12 because we start counting at 0. Um, and does that make sense? Um, the a sub I one is a bit more fun. Well, so what we have here is it looks like there's something times e to the I. Okay? Because if I is 0, e to the 0 is 1. If I is 1, e to the first is e. If I is 2, then e squared is, well, e squared, and so on. But the terms alternate in terms of their sign. So they go from plus minus, plus minus, plus minus. And the way that we can get that is to have negative 1 to the I out front. When I is an even number, so 0, 2, 4, and so on, negative 1 to an even power is 1, and so we have a positive. If I is an odd number, then we would get negative 1 to an odd number is negative 1, and that would flop it negative. And in this case, we could write it, oops, we could write it in that form because both of the exponents happen to be the same here. Um, and so that is our formula for a sub I. So yeah, so that problem is basically about kind of pattern recognition. Um, and yeah, does that make sense? All right. So um, let's go back to what was I doing? The integral of cotangent. So the first thing is just to rewrite it in terms of sine and cosine. And then we'll make a u substitution. oops, if u equals sine x, then du is cos x dx. And then we can just substitute because this is exactly right there, and this is exactly right there. So this is just literally the integral of du over u, which we know is that. And then we just need to plug in our absolute value. Okay, so that one was relatively easy. Works almost exactly like the integral of tangent. This one, ironically, is slightly easier because you don't have that pesky negative like you did with the integral of tangent, but whatever. What's a minus sign between friends? Okay, then the other one that's a little bit more fun was the integral of cosecant x. And the trick we have to pull is to multiply by this funky fraction. So it's sort of the same idea as how we did the integral of secant by multiplying by secant plus tangent over itself. And this just turns out to be the version that we need for this guy. And so if I multiply that out, then I've got cosecant squared x minus cosecant x cotangent x all over cosecant x minus cotangent x dx. Then I'm going to let u equal the denominator. All right, and now we basically have to remember what's the derivative of cosecant? It's negative cosecant cotangent. And the derivative of cotangent is negative cosecant squared. But because I have a negative in front already, it becomes positive, and all of that is dx. Well, if you look again, this is exactly what we have here, and this is exactly what we have here. And so this is literally du over u, which again is that. Oh, let me scroll up a little bit. There you go. All right, that's it. So these are both good examples of u substitutions. Obviously, there's more in those exercises. So if you guys have a look at the 6.1 problems a bit, obviously for Friday in class, what I'd like to do is um, polish up any cobwebs or any last lingering problems from everything but 6.1, and then we'll finish the day. So maybe we'll split the day about half and half. Problems from 6.1, and yeah. Okay. Well, I guess it's 8:50, so we should probably quit. Do any of you guys have a class right after this? Just out of curiosity, figure I should have like discovered that like at the very beginning of the semester, but um, yeah. Um, all right, so we'll go ahead and quit the stream here, um, and I will see you guys on Discord if you have other questions. I should be around on Discord most of the afternoon and evening. Got some things to take care of this morning. Um, and yeah, sorry, Zach. Stream's over. Um, yeah, so if you guys have other questions, hit me up on Discord in the text chat, and then we can talk via voice. And I will see you guys on Friday, if not sooner. All right, well, have fun with Spanish, Willie. See you guys Friday.